Yeah.
Okay,
I mean,
so
oh yeah, go. Yep.
yeah, I was just gonna say maybe we start now.
Yep.
We have 21 people, and that's probably all we can expect given the hour. So we have our third and last lecture by Meera Parish, which is our last lecture. Okay, that's my YouTube. Okay, so take it away, Meera. Thank you again for coming to lecture and accommodating us with your schedule. And we'll look forward to hearing about BCS-BEC and the imbalanced physics.
Okay, great. Thanks, Leo, and thanks everyone for joining it at this Friday afternoon or Friday evening, your time. Yeah. So what I was going to continue talking about was I'll continue our discussions about the crossover, and then let's see how we go from there, like whether we can explore extensions of that depending on the time today. So what we discussed last time, or what we finished the lecture with last time, was this idea that we could use a single wave function. What was originally written down for a superconductor, the so-called BCS wave function, we could use this wave function to describe the whole crossover from the kind of fermion pairing you had in a superconductor on the BCS side over here, all the way over to the BEC limit of tightly bound pairs of fermions. So we could use the same wave function, implying that you have a smooth crossover from one limit to the other. And we also discussed how, at least in terms of the two-body physics, is sort of linked to whether or not you had a bound state at the two-body level. So whether on the BEC side you would have, well, it corresponded to positive scattering length corresponding to a bound state, while on the BCS side it corresponded to negative scattering length in the experiments where you don't have a bound state. But in the many-body case, when you have a Fermi C, you do have you can have pairing at the Fermi surface, like as we were discussing. Actually, one thing I should mention, so this is the case in the 3D Fermi gas. I don't know, probably, well, Randy mentioned 1D, but also there are other scenarios where, in the case, say, where you always have a two-body bound state, like this could be in lower dimensions, like 1D or 2D, or in, say, solid state systems, say, where you have bounds or bound pairs of, say, of a positively charged and a negatively charged, so electron and a positively charged hole. So you have this kind of bound state there, this exciton. In that case, you can actually still have a kind of a BCS to BC crossover, because in that case, what happens is the way you drive this crossover from this side over to this side, from the BEC to BCS, is you actually, all you need to do is just increase the density so that eventually here the pairs we're showing becoming larger, but you can think about increasing the density so that these pairs start to overlap, and eventually they overlap so strongly that starts to interfere with the usual two-body bound state, and now you have actually Fermi statistics being important, and you can actually drive your system to the BCS side that way as well. So there is this other way, even when you always have a two-body bound state. So it's not just, you don't just have, not having a bound state is not a requirement to get the BCS side, the BCS limit. But in this case, in the 3D Fermi gas case in cold atoms, that's the case that we're considering here, this scenario. Okay. All right. Hopefully that makes sense. Okay. So what I was going to do then, I was going to now come to actually putting some more mathematics on what we were discussing. So what we want to do here, I want to show you actually how, if we start from our ground state wave function here that we wrote down, that I told you describes pairing in both limits, and now if we want to actually just look at actually how this behaves. I sketched out some of the behavior last time, but if you wanted to show more formally how that comes about, what you need to do actually is you need to consider the free energy, which is the expectation value of your Hamiltonian. And then I'm working in this grand canonical ensemble, so I have a chemical potential. So I'm interested in this quantity here. using this this variational wave function, okay, this BCS type wave function. And so if I go ahead and I calculate this expectation value, so I have a term that's due to the kinetic part and my chemical potential involving my VK squared. I have another term involving my interaction. So remember, this is where we're assuming this kind of toy short range interaction, which is just described by this constant or this interaction strength G. And then I end up with this term here. Okay, so this, in principle, I have these two terms. So one involving, well, this is essentially what we'll see is the term involved in fermion or pairing between fermions. And there's an additional term that you find involving just the V's. And this one actually is just like a sort of a mean field kind of Hartree type term. So in other words, you remember that this sum over VK squared was just that just gave you the density or the number of particles in that state. And so this term essentially is a term that's like G times density squared here, or density of each fermion squared. Density in each spin state, so. Right. Okay. So the one thing I should mention, okay. Yeah, so now at this point, this is why, I spent a bit of time on normalization, renormalization, sorry. Okay, sorry. Okay, so at this point, one of the reasons I kind of talked about, this how to, renormalization, how to relate this bare G, if you like, this toy G to real scattering parameters like scattering length, is that what you remember? We argued that this G here actually goes to zero if I take the range of my potential to zero. So if I take the cutoff on my momentum sums to infinity. So what this means then is actually, if I want to actually if I'm trying to describe like the physical, system, the large scale low energy properties of my gas that only depend on the scattering length, don't depend on the microscopic details of the potential. And remember, this is a toy potential; it shouldn't actually play a role. What you can argue actually is that this term I can just drop. This should go to zero because G is going to zero here. Okay. Because this term is just the density, and then as I send G to zero, this whole thing goes to zero. So I can actually just drop this term here, and I only have this term. And the reason I have to keep this term is that actually this, even though G is going to zero, this term now also depends on the cutoff. Okay, so this term would diverge. So this whole term here is actually finite. It's a finite if I have G and this term here. Whereas this one it vanishes. Okay, does that make sense? Any questions at this point?
It seems like the second term also has some K dependence. It's just the fact that it goes to zero, the fact that all the V's are kind of the occupation, and at large enough lambda, there's like zero occupation of fermions, we hope. So that's kind of, that will always be finite.
Yeah, I mean, I think it's also a question of how this V kind of depends on K. So the fact that you have on one hand you have a VK squared, and the other hand you have VK UK, and it turns out this one goes to, well, this term goes to zero with K faster than this one. Yeah. So as we'll see, so this term essentially is okay, yeah.
I mean, you could also say, couldn't you also say that the term you threw out, I mean, it's just a shift in the definition of chemical potential which is density dependent. It's just a Hartree shift of the chemical potential, which you don't know anyway. So you're going to adjust the chemical potential such that the number is what you want. The average number is what you want.
You could argue it that way. I mean, I think the only thing is, so when you come to say doing spin imbalance, then it starts to matter this kind of term once you start having first order phase transitions.
Right.
So in the sense that, I mean, so then it becomes a question of whether you can throw this out formally like this or not, if that makes sense. So maybe let me put it another way. If I go ahead and I do my calculations for spin imbalance in 3D, I'm fine with dropping this term for this very reason, because of the type of state that I've written down will give me essentially gives me a zero Hartree term. I need to write down a different wave function if I want to actually have a Hartree term that involves a scattering length. But if I were to go to 1D, for instance, then you find that even at this level, because this, in that case, you can argue that, well, as you know, that this G will not disappear. It actually doesn't renormalize to zero. And then in that case, I do actually have to keep it if I'm looking at first order phase transitions. So that's what we were finding a few years, well, more than 10 years ago now. Wow, I'm getting old. Yeah. But yes, no, that's yeah. But that's also a good point, that if say I had to keep this Hartree term, it does indeed just shift the chemical potential. Yeah. But yes, anyway, for this case though, there's no Hartree term. It just goes to renormalizes to zero. Yeah. Any other questions from people, or shall I press on? Yeah. So so the only other thing I should say here is that you notice that what I've implicitly assumed, or what I've been assuming so far, is that these parameters, these UKs and BKs, are actually real parameters. Okay. I mean, in principle, they can be complex. In fact, in general, they are complex. But I can assume in this case, for this sort of S-wave pairing case, that they're real. Just because if there is no kind of there shouldn't be any kind of dependence on angle or momentum. Well, yeah, any kind of angular dependence, and also, I could make this complex, but I can always absorb any kind of phase here in my definitions of my creation operators. So you can always choose your U's and V's in this case to be real. There's always a way you can define it. So that's the case. All right, so that's just a side note in case you're worried about why I'm assuming that, or wondering about that at some point. Okay, so if you want to, now what you want to do is you want to go ahead and you minimize this free energy. And you see, this is we're doing a variational approach here. After all, we want to minimize our ground state energy with respect to these variational parameters, these UK and these BKs in my wave function. And I'm going to do that in this case at fixed chemical potential. Okay, so, all right. And now you might remember that we have an additional constraint, which is that the UKs must satisfy this normalization constraint. If I want the wave function to be normalized, I require my UKs and BKs to the sum of these squares to be 1. Okay, so I have to keep this in mind when I minimize this free energy. I can't treat these as completely independent from each other. So the simplest way, if you're faced with that, the trick you usually do is you say, well, what I can do is I can say, let's say that BK is sine theta k, and UK is cosine of theta k. So by defining them this way, then I automatically satisfy this normalization condition. So that's one way you can do that. You can just define them like this in terms of this theta now. Okay. And so now if you bear that in mind, what you can do now is you can go ahead and minimize. Okay, so take and set it to, so you want to essentially minimize this with respect to this theta k here. Okay, and what you find now is that if you go ahead and do this is an exercise. You find that you end up with this equation here. Okay, so I have my kinetic part, and then I have UK squared minus BK squared. Oops. And I have a G over BK prime, BK prime, and that equals 0. Okay. All right, so that's my equation that I get from minimizing it. All right, so that, and okay, so the reason I'm going through this whole process is what's interesting is you can see that if I take the limit, in the limit where I have, if I assume that VK is small, so I'm taking the limit where it's close to 0. So that's the limit where I'm in the BC regime, because that, so you remember last time, so this, okay, so I have this, if I'm going from, so the BEC regime is basically where I don't have any Pauli exclusion, there's no kind of Fermi, any Fermi step function. I'm very, very far from being, completely occupying any of these modes here. Okay, so and where VK actually approaches or becomes proportional to the relative pair wave function of my two-body bound state. Okay, so in the limit, so what you find in the limit, you actually recover the two-body equation actually. So the equation for two particles. So what you have is you have 2 EK in momentum space. So it's a sort of momentum space version of what we were discussing previously. Okay, so if I just write down, so I have, yeah. All right, so what you have here is, okay, so you have your kinetic part, it's just in momentum space here. And I have now, this is my interaction, like my short range interaction potential in momentum space. Okay, so where I'm scattering my particles into different momenta. And then I have, okay, so this now plays the role of the energy in my equation, this 2 mu times my wave function here, or my VK here, which is my two-body wave function. So what you see now is, okay, knowing now that you've recovered this two-body equation, what you can automatically say is, well, therefore, okay, so actually this 2 mu on this right-hand side here is nothing more in this limit, is actually just the two-body energy, which is the two-body binding energy. Okay, so this is, if you remember, that was, in this case, it was h bar squared over, okay, so it was 2 mr, so actually the reduced mass is just, if I put in what the reduced mass is for, well, this equal masses, it's just m times a squared here. So, that's a minus here. So what you see just automatically from looking at this, that the chemical potential in this regime, or rather twice the chemical potential, tends to the energy of the two-body bound state in this limit in the BEC regime. Yeah. Makes sense.
Can I just ask a question, just making sure. So from the left to the right, we're basically saying that U is approximately 1 and we're dropping V squared terms, right?
Yes, that's right. Yes, exactly. Yes, that's correct. Yes, that's right. Exactly. Yeah. Okay. So he's saying yes, exactly. Yeah. Keeping the lowest order term in yeah. That's correct. Yeah, so term is linear in VK essentially. So yeah. Any other questions about that? So it really is just the leading order term. And it kind of makes sense. So what's happening then is, if you go to that limit and the BEC limit, now the chemical potential is going to be dominated by, beset by the pairing in your system, in the sense that if you add a fermion, or rather you have to have 2 fermions, they're going to go into this bound state, which has this energy of the minus EB. Okay. Now, okay. Now, one more thing. So in general, what we can do now, if we define, and it's become clear, this is actually going to become the so-called gap parameter. But here, what you can say, okay, let's suppose if I define this quantity here. Okay, so that's, and okay, this is something that one will realize is important after you kind of define it. But yeah, so there's basically, it's taking this object here and saying, let's define this to be this quantity here. We know that this is something, G doesn't depend on momentum, by construction. Okay, in principle, there's a cutoff here, but basically this is now just some constant, or some constant parameter here, which is delta, constant real parameter. Okay, and now I'm just going to, just for convenience, I'm also going to define this parameter CK, which is just the kinetic energy involving mu. So this is sort of a standard way of standard kind of definition. And now if I take, okay, let me call this equation double star. Okay, so if I take now this equation double star, so then this equation double star becomes, you have, right, then gives, yeah, so if I'm just rearranging this, I have UK squared equals delta to CK, sorry. And remember, so remember how we defined our UKs and BKs. So that's just actually just from this, that is actually just, I can just rewrite that now in terms of sine 2 theta k and cosine 2 theta k's. Okay. So actually what you can do now is you can say, well, I know that these two, once again, these are sine and cosine. I know that they should add up to 1, or the squares should add up to 1 rather. So I can use that therefore to determine what this sine 2 theta k is. And that's just, well, this delta divided by the sum of these two, which should, since you know that these, oops, the sum of the top and the bottom. Okay, so we know that, okay, so this is basically just, yeah, so taking these two, squaring them, and so that, and then dividing by the square root of this. So then by construction, you know that this, so cosine will just be the same with CK on top instead. Okay, so that's, whoops, and I think I meant, yeah, no, that's correct. Yeah. All right, so now and then finally that means that you've accessed what this UK BK is, which is just delta over 2 times this. So, okay, so that's just making use of what this is here. Okay, so now then, okay, you can take this and put this in here. So I'm basically deriving the gap equation is what it's going to come out to be. So I can take this now, put this in here, and hang on a sec.
Yeah, that makes sense.
Yeah. Cool. Yeah, I was kind of hoping to put it all on one page, but I always seem to write bigger. Okay, so therefore then, yeah. And okay, let me write down the last thing, which is basically that I can also work out similarly what this guy is. Yeah, this cosine 2 theta k. Okay, and that just, hang on, let me just write that here for completeness. So that one's there, and I also have sine, oh, sorry, cosine is CK over. All right, so I can take these now and I can insert them into my definition for delta, and I can also use the fact that I know that the density is related to my sum over VK squared. Okay, so finally then what I end up with, Actually, I think I can do this. Yeah, sorry. I'm just rearranging my slides here. Okay. Let's put this back here. All right. So finally, what I end up with then, if I insert this all, is two equations. So I have one which is where I've inserted into the definition of delta, and I've removed the powers of delta. So I just end up with this. Whoops, sorry. Yeah. Okay, so that's one equation, and that's this celebrated so-called gap equation, which actually allows you to, just by solving this equation, you can work out what this delta is for a given chemical potential and a given scattering length, and even interaction. And likewise, I also have a so-called number or density equation, which allows me to work out what the density is once I know my delta and for a given chemical potential. Okay, so let me just write that out. Okay, so that's my so-called number equation, it's called. So these are these two equations that you would solve to actually work out how this behaves throughout the crossover. Okay. Any questions at this point?
Is there any way to see why delta is a gap at this point?
Well, okay. So I would say, okay, what we can see, I mean, yeah, no, that's a good question. So, okay, let me put this in inverted commas. What we can say at this point, what we can say is that now we know from the definition of delta, so we define it like this, where it's in this combination of UKs and BKs, and you can show that this combination of UK and BK is just the expectation value of this C dagger K up and C dagger minus K down here. So what you can see at this point is that this delta is related to the pairing of these two fermions, the up and down fermions, and K and minus K. So gives a measure of pairing. But what I'm going to show now, well, okay, so and also you can see also in the limit where I take VK to be very small, I drop this UK term, you can also see that it's related to the relative pair wave function, the BEC limit. Okay. Okay, it's also related to maybe I don't want to go into this, but it's also related to the what's called the tan contact, which also gives a measure of the density of pairs. But okay, so at this point though, you're right that it's not at all obvious why this is a gap, although what you can see here certainly is that, okay, there is what looks like, this combination of kinetic part plus delta squared. It looks like there's some kind of, it's appearing in some kind of like dispersion here. What we will show now, okay, so this, I showed you one way of thinking about the problem. What I'll show you now is actually there's an alternative way, equivalent way, where it will become clear now why this is this a gap, why this corresponds to a gap in your excitation spectrum. Yeah. Any other questions at this point? The only other thing I would say is remember that what we want to do at this point is we will replace G. If you just in case, remember we can replace G with this equation here. This is just me rewriting what we had written before in terms of for the case where we have equal masses, and where this EK is just h bar squared k squared over 2n. Okay. So that's just the equation I had before, this Lippmann-Stringer equation. Okay. Yeah, so what I can do, okay, let me just take this. Put it over here. All right, more or less works. Okay. So I just have a plot at this point of how this delta, this measure of pairing and this chemical potential varies as a function of the scattering length. So here, remember, this is the BCS side in this case, and this is the BEC side. And so what you see here is the chemical potential on as you go into the BCS limit, that approaches just approaches the Fermi energy, as you would expect. So it's approaching what you would expect for an weakly interacting or non-interacting Fermi gas. Yeah. Okay. Whereas as you go down towards the BC side, then that's approaching the binding energy of the pairs here. Okay. Or rather the negative of the binding energy of the pairs here. And likewise, you see the gap here, this pairing delta. It starts out very small. In fact, in the BCS limit, it's exponentially small. You can show that. So in the BCS limit, the KFA goes to minus infinity. So yeah, like I said, we have, okay, as I mentioned, we have this mu equals EF, and also we have this delta EF, which is roughly, okay, there's some, in principle, there's some prefactor here, and then you have a exponentially small gap. Exponentially, oops, sorry, got a vector T. Yeah, so it exponentially depends on my interaction, my scattering length here. So very, very strongly suppressed. Whereas out here, it actually, it grows as you might expect as you go towards the BEC side. It becomes larger and larger because it's, pairing becomes stronger and stronger here. Okay. All right, so any other questions before I now show you this alternative approach?
There is a question in the chat.
Yes, okay, I can see it. Yes, thanks. Oh, okay. Oh, okay, yes. You discussed, Leo, did you discuss this equation? I see.
Well, I talked about, during discussion, I talked a bit about it. And in particular, I pointed out how for repulsive interactions, it just gives you that the scattering length, the biggest the scattering length can be, is actually just the effective range, which is 1 over lambda. But the range of the potential, which is 1 over lambda. And it's only in the attractive case do you get this divergence.
Right, yeah. Yeah, so then, yeah. Okay, cool. So any other questions at this point? Or everything should press on to the excitation spectrum. All right.
Just to make sure, is the touching point between the chemical potential and the gap exactly as the scattering length diverges?
Yeah,
overanalyzing this plot.
No, I'm kind of I didn't think so. Yeah, not quite. Yeah, no, it's an interesting observation. Yeah, so not quite. Whoops.
Okay. So there's no physical significance of the matching of those two energy scales, or is there?
Not as far as I know. But there will be. We'll show in a moment that there is going to be a. Hang on, there will be a physical significance of when the chemical potential. Let's see if I draw a zero here. Yeah, when the chemical potential goes through zero, that's on the other hand physically significant. this because that actually corresponds, well, what we'll see in a moment, that actually corresponds to a qualitative change in the excitation spectrum. Yeah. Okay.
Maybe this is getting ahead of things, but like, is there a significance to the fact that that occurs on the where the scatter where A is positive?
Is it? Yeah, I think it's a good point. Yes, yeah, in some sense, yes. Because it's basically telling you when the system, if you like, is becoming more bosonic-like compared to fermionic-like. So where you're kind of losing your Fermi surface, and so you would expect that to occur on the sort of for positive scattering lengths. Yeah, on the BEC side, if you like, of the resonance, Feshbach resonance. Yeah. Okay. All right. So yes. So sorry, I'm kind of. Hopefully this is. I thought I'd try and do this very carefully, but okay. So the alternative derivation of this. Okay. I mean they're both kind of mean field, but this is sort of more a standard type of mean field approach. Where you don't actually, I mean, it's equivalent to in the ground state to having to writing down your variational wave function. But what it allows you to do is more easily see what the excitations are on top of this ground state, which is coming back to this whole idea of the gap. And also it allows you to go beyond the ground state and consider, say, finite temperature, and also potentially even consider corrections. Well, okay. See how you could include corrections to the mean field approach, because this is an approximation. All right. So what in this case, what you do is you say, well, let's assume that pairing dominates, so pairing between fermions dominates in your system. That's the dominant kind of effect of interactions. So such that what we want to do is describe it with a mean field, so that's such that we what we're going to do, inspired by what we had before, we say, let's suppose now I'm going to define a mean field called it's going to be the same delta, which is now the average, once again, of this, taking this average of k and let's minus k here, whoops, and there's an up and down here. So I'm going to define my kind of mean field as this expectation value for zero momentum pairing. So this is zero momentum. I think Randy might have talked about finite momentum pairing. That would be where you corresponding to the FFLA. But that at least for the case where you have no spin imbalance, that's not the favored state. There's no reason why. That's a higher energy kind of configuration. So you want to take pairing at zero momentum. So I define this mean field, okay, so I define this expectation value. And what we're going to assume then, we're going to assume that, so we can write out now operators. So if I now take my G, let's take this, just the operator version, so not without the expectation value. Yeah, so this is like a part of my interaction that I have in my Hamiltonian. So this is, operators for a pair at any momentum in principle. Yeah, so this is a term that appears in my Hamiltonian. And I'm going to say, well, okay, well, first, let me just write this in terms of this, mean field. So this is just a bit of rearranging here. So I say, well, okay, I can write it like this. So this is where I end up with this delta if this pairing, this finite momentum pairing, or center of mass momentum is zero. Okay, so I end up with this. So I can write it like this. It equals delta if Q equals zero, and plus what I call this correction, this operator correction here, delta Q. And so where this sort of correction, if you like, this is literally, okay, I'm just rewriting here, is literally just the difference between this delta term and this one here. So I'm just literally just rewriting it in a, so here's my, oops, here, and then I have this term here. Hopefully I have all the signs right. Yeah. Okay, so this is, I'm just rewriting my stuff. And the point now is that what I'm going to assume is that this term is small. Okay, so that's the whole idea. So I'm going to rewrite my Hamiltonian, assuming I can discard higher order terms of this. Okay, so this is, so yeah, like I said, assume this is small.
Can I just ask a clarifying question?
Sure. Yeah.
So in principle, we define delta to be a number, but
Yes.
the left
Yes.
side clearly is an operator. So should I think in terms of like the mean field, that at the end of the day, I'm always interested of applying this to a particular state where that operator on average takes some value, and then there's fluctuations that I'll keep as an operator for now? Is that sort of the motivation?
You can think about it like, yeah.
Thank you.
Mm-hmm. Yeah. But at this, yeah, so at this point, literally I've just rewritten it, but yes, exactly, yeah. So now, now what we want to do is we expand the interaction part. So let's see, call the interaction part of my Hamiltonian, let's call it H int. So, okay, so, all right. So, okay, so what we can do is we can, let me just write, okay, let me just copy this here. So remember we had this term here, okay? So I want to expand, I'm going to rewrite this in terms of my mean field, my delta, okay? So that corresponds to, what it turns out that corresponds to, I could, this sum over Q here, and I have this delta. 0, and I have delta, this one here. All right, so it turns out, I mean, you should check this for yourself, but this is how you can write it. And now, yeah, so now what we're going to do is we're just going to expand this and drop any kind of quadratic terms in this guy here. So I have my delta squared here. Oops. And my delta Q0 here, and then I have just this fluctuation term here. And remember, actually, these can actually have like conjugate, and I mean these can have, I can take the these involve both C and C dagger, so I should have both of these here. Okay. All right, and then finally, what you find if you keep expanding that, so this interaction part then is just given by, so I have my first term, which is just, yes, okay, hang on. So what you see is that, let's see if I can do this. Yeah, okay, so what you see now is that, yeah, okay, let me just stop this. So there's going to be an additional term from this here, this delta squared term that will essentially, well, I think you'll end up with a factor of 2 delta squared over G. So what you find finally, once again, this is something you should check or clarify with me if it's not clear, but you end up with this kind of expression here. Oops, let me move this over. Minus delta. Yep. All right. Yes. Okay. Good. And so now what you can see is that the nice thing about this is that I've okay. So we just we've introduced this mean field, and now we've actually made this just as a function of 2 operators rather than 4. Okay, so you just have, so that means now you can actually, you have a bilinear Hamiltonian, you can actually start to diagonalize it. You can actually solve this Hamiltonian. You've removed the 4 operators that were causing you problems and making it difficult to solve, converted into 2 operators instead.
I think it's a simple thing, but you probably
Sure.
want to have a summation on Q in the second term where the Kronecker delta is.
Hang on, let me just see where I have.
Right.
Yes.
Because then that removes the Kronecker
this one
delta
here.
and gives you the, yeah.
Yes.
Sorry. The bottom equation on the left, the very bottom, second term of the bottom equation on the left.
Yes, you're right. Yes, sorry. I don't know why I dropped that. Yes, you're right. Hang on, let me just. Thanks. Yeah. Cool. All right, that should be complete.
Yeah.
Okay. Any questions about this? Yeah. So finally, then, if we put that in here, we have mean field Hamiltonian. Whoops. Okay, so where we write it like this, my delta squared, and then I have like a part where now I'm going to define, okay, let me just write this first. I can write it like in a sort of matrix form. My deltas here. Oops, wrong way. Okay, and then I have this term, and I'll just define what these sides are in a moment. Okay, so where we have the psi now is, or rather the side, let's say the psi dagger now corresponds to a vector involving these. So involving these operators here. Okay. Cool. Right. Okay, so just a thing to note here. So all I've done really, I've put this in here. I've put this back into the original Hamiltonian. And now, so we have a kinetic part as well. And then all I've done to get this 2x2 matrix is I've done an anti-commutation of my kinetic part, my C dagger C, which is why I have this additional term here from the anti-commutation relation. So just so I can put it in this form here, because you notice that this term will involve a C dagger rather than a C dagger C if I expand this out. Okay. All right. So then what you can do then is you can diagonalize this, and this is I'm going to leave this as an exercise. You can diagonalize this using this Bogoliubov transformation. Okay, where my new kind of operators, which are related to my old operators. And this is actually, what you'll find is actually, these are exactly the same V's and U's that we had before. So that looks like a V. Yeah. So that's something you should just check. If you haven't already done it, it's a good exercise to check that this actually works. Okay, so if you make this transformation, so it's actually a sum involving both C up K and C minus K down. Then you find that you can actually write this, finally this mean field Hamiltonian in terms of these new parameters. So you have, once again, this term here, this constant term, delta squared, plus, okay, so we have our original epsilon k minus mu, and then we end up with another term here. Hang on, I'm running out of space. This is any problem with this technology, I think I write too big. Yes. Okay, I think I can even be cleverer. Maybe. Okay, I'll resize it. So okay, here's my transformation. All right, so I have this and I have term involving my new parameters here. Yep, and where this ek now, this new parameter is exactly this psi k squared plus delta squared that we encountered before. And this is always, I mean, this is positive. So this is actually, so what you see here, what you'll see, so this is always positive. So in the ground state, these operators here, there should be no occupation of these operators, right? So the ground state should be where this term is gone. So the expectation value of this is gone, and you just have this term here. So the ground state energy is just given by this part here. So this automatically gives you the excitations on top of the ground state with this excitation energy, capital EK. Right. Are there any questions about that?
Good. Just making sure I understand. Like we started in the regime where we assume that the pairing dominates. So if I understand correctly, that should correspond to the BCS regime, the BEC regime. But this derivation feels what we usually do when we're trying to understand superconductivity.
Okay. Yes. Sorry. Yes. Okay. Maybe I should be clearer what I mean by pairing dominates. I mean in the sense that it dominates over any other. I mean, okay. The main effect of interactions is to pair up the system. There's no other kind of let's see. So no other kind of correlations happening. Like there's no, say, like you can think of other types of, if you like, order parameters or orders or types of like, for instance, magnetism, or I'm claiming I'm going to throw out anything, all of those terms, throw out any other possible kind of ordered phase. I'm going to say my phase is going to be only have my ordered, if you like, my ground state only has pairing correlations. I'm going to forget about any other correlations. If that makes sense. Oh, so that's the only kind of mean field term I keep. So it doesn't have to mean that the pairing is very strong. It just means that it's the only kind of, I mean, just like in a superconductor. So you don't have, we're saying that we only have pairing between electrons. We don't have any kind of magnetic order or anything like that. That makes sense.
It does. So I guess like in this picture, like BCS to BEC, like, should I just think that this applies kind of at the two edges? Because we're dominated by this pairing, or am I missing some ingredient?
Okay, so I think, yeah, so really we're imagining that this mean field type, okay, it's an approximation, but this mean field type picture, this pairing, or if you like, this pairing field or pairing autoparameter is there throughout the crossover. All we're saying is that what this mean field kind of approach is saying is that this is the dominant let me put it this way. I could have chosen another type of field, like, I don't know, maybe I could have said, I want a field where it's CK some other field. I could have taken some other expectation value. But I've chosen this one. So that's the thing. I made a choice and I've said this is the important physics in my problem, which is pairing. There could be other physics, but I'm going to say that's irrelevant. Yeah.
Okay, so even in the BCS piece where the delta itself is very small, we're still assuming that delta is much bigger than everything else. So broadly, we expect this to kind of capture the entire crossover.
Yeah, I mean, or rather, yeah, we're assuming at least there's a phase where we have, even though delta is small, I have if you like, a macroscopic occupation of this field. Right, yeah. Just like in the BC case, I have a macroscopic occupation of the whatever cubic zero or the ground state. I'm saying that I can define a field that's going to be a macroscopic occupation of this particular field. Even though it might be small, as you say. Just like if you had a small condensate fraction or something, but it's still there. Yeah.
Awesome. Thank you very much.
No worries. Any other questions?
I was just going to make a comment, maybe, if there are no questions.
Yeah,
So
sure.
this mean field Hamiltonian, the first two terms describe the ground state energy. So meaning you have a vacuum of gamma particles. That is the BCS ground state. So then the first two terms is the ground state energy. And if you actually work out that sum in the second term of that mean field ground state energy, and then it'll be a function of delta only. And if you minimize that over delta, they'll give you exactly the gap equation that Meera has already derived. So
Exactly, yeah.
it's everything's self-consistent. Like you can minimize this energy over delta and get that exponential expression for delta.
Yes, exactly, yeah. Indeed, and indeed that first term is basically, I mean, you'll find that it should be equivalent to this term actually that we wrote down originally. Yeah, as well. But like you say, you can write it in terms of delta and it should be the same. Yeah. Yeah, no, that's it. Yeah, thanks. Yes.
And maybe another note about it is, if you actually work out that sum of that second term, it equals to delta squared log delta over mu. And you can notice that always has a non-zero minimum for delta. The saddle point of that always has a solution at non-zero delta because we're at zero temperature. So what it says is at zero temperature, within this, within this purely superconducting channel description, there's always superconductivity at zero temperature. There's no phase transition for any G. As you vary G, there's always non-zero delta. Yeah, exactly.
Mm-hmm. Yeah.
And that's because the second term is delta squared times log delta. And log delta is always negative for small delta. And so then there's always a downward cusp. It's always downward facing. So then it has a shape like Meera just drew.
Mm-hmm. Yeah, no, exactly. Yeah. Mm-hmm. Yeah, exactly. So, where am I? So, yes, let me just take this over here. So, all right, yeah, so with my mean field, okay, so my mean, yeah, exactly. So, as you say, mean field, this one, as Leo is saying, okay, so so in the ground state, I need, this term is gone. And in that case, if I minimize with respect to delta, that indeed gives me my gap equation. Yeah. So where was I? Yeah, let's go. Yeah. Just like I had before. And likewise, if I want to work out what the density is, I can also take the derivative of this with respect to the chemical potential. And that will also give me the density equation. So it should all be kind of there. Yeah. Okay. Yeah, so what's actually happening with these quasi-particles here, or these excitations here, is that they correspond to the case where you break a pair. So that's what the sort of pair breaking excitations. So if we come back now to this, this excitation energy here. Okay, so that was this EK equals square root. Let me write out what this CK was. Okay, so we have this excitation energy. So now if I think about plotting it, because this is where the kind of looks interesting as well. Plot it as a function of K. Now you see that if I have a positive chemical potential here, let's consider that first. The shape of this looks like the following. So I have, yeah, okay, more or less draw it. Okay, that's meant to even as a function of K, even around the K equals 0 axis. But so it has the following shape where now this gap here in the spectrum is just given by this delta. So this pairing gap. So that's the origin of this term for delta here. You end up with a spectrum exactly which has a gap at least the point where well, this point in general, at the point where the chemical potential for a positive chemical potential, it's where this term is 0. So it's where the K is, oh, okay, let me write it down. So this is where roughly K is given by square root of 2m mu here in general. So in general now, so in the BCS limit, you know that mu approaches the Fermi energy, so that in the BCS limit, this minimum here, where this minimum in the energy occurs, the excitation energy occurs, is just at the Fermi momentum Kf. But in general, in the crossover, it occurs at this finite, or this positive K here, okay, given by the chemical potential. So what you're going to see then is that if the chemical potential is negative, on the other hand, the excitation spectrum actually changes qualitatively, in the sense that now we no longer have a minimum at finite K. It's only at 0 K now. So we have something like this, right? So once that changes sign now, and now the gap is actually going to be given by, instead of just delta, it's actually given by delta squared plus mu squared, okay? And it makes sense, so you can see actually once I go into the sort of deep BEC limit, what this gap is going to correspond to is well, it's going to be dominated by the chemical potential. And so that gap is just going to be exactly given by the binding energy of my tightly bound pairs. So you can see now you're crossing over from like well, this is sort of a spectrum where there's really certainly in the BCS limit, you really see the effect of having a Fermi surface. So this minimum it's occurring at the Fermi surface around Kf, minimum in the spectrum, all the way over to the BC regime, where now actually this gap you're talking about, this pairing gap, is really just the energy required to break a tightly bound molecule. Yep. So what you see actually, what's important now is this, like I said, there's a qualitative change in the spectrum, between these two limits, at mu equals 0. Okay, so that's the point where this spectrum, this excitation spectrum changes, and from having a minimum at finite K to having a minimum at K equals 0. So this is actually what's often been referred to, if you wanted to define a crossover point. I mean, it's a crossover, right? So it's hard to, there's no real sharply defined transition. But if you wanted to define a point which is the crossover point, it would be this point here, where the excitation spectrum changes qualitatively. So this is remember this is and remember this is different from the unitarity point where the scattering length diverges. Yeah, and as was kind of being pointed out earlier, this occurs on the side where the scattering length is actually positive. So mean field theory, I mean, as we showed in the picture, that just gives us the crossover point is roughly at, I think it's around 0.55. So if you look at the figure. But this is, yeah, like I said, it's not at unitarity. But I think if you do a more careful calculation, actually, even if you do a more kind of sophisticated calculation, it's actually not that far from this mean field value. It's still around this point, around 0.5 or maybe, yeah. So it is generally expected to be around this point here on the BEC side of this resonance. Yes, but like I said, as we were discussing before, while this is, so while in the many-body system, the crossover point is not it occurs, not at unitarity, but when the chemical potential goes to zero, what you find is actually that the unitarity point is still special in the sense that, oops. So the point where this goes, the scattering length diverges, still special in the sense that it's universal and scale invariant, like we were saying before. Because now, what that means now is that the length, any kind of length scale associated with your interactions drops out of the problem. It's gone. And everything now just scales with the density. So as I was mentioning, now you have a chemical potential that just scales universally with the Fermi energy, or for instance, you might have pressure or energy that also, like say, pressure that of the gas. Say, I mean, there are all sorts of thermodynamic quantities that also feature this this universal parameter. So this would be where this is the pressure of the non-interacting gas here. And so where, yeah, this C is really just a universal constant. Yeah. And so this is something that you can now go ahead and calculate, well, or measure actually, as it turns out, the best. So the best estimate for this is, I think, around 0.37, if I remember correctly. So the best estimate for C is around, yeah, like I said, whoops, let's see if I can, 0.37. This is from MIT experiment. So this is Martin's Williams group in 2012. And this is the thing about mean field. This is where you can see that mean field is not perfect. So mean field theory, on the other hand, would give you something that's about 0.59, I think. So it overestimates pairing. So that's actually a general feature of mean field, is that it overestimates, how, well, the mean field, the actual, yeah, it overestimates what it's trying to describe here, the order parameter here. Yeah, so what's kind of nice actually is that, sorry, I'm just going on about this for a bit. What I was surprised to discover is that actually all these people working in nuclear physics, it turns out that in neutron stars, you have like pairing between neutrons in principle. There's all these discussions about neutron pairing, superfluidity, and they're actually very close to this regime here. And so they can basically take a lot of these results from calculations and measurements from a very low density Fermi gas here, and apply it to a very high density neutron star, just exactly because of this universality. In some sense, if you have a system that only really depends on your scattering length and no other kind of details of your potential, and then you tune to this regime where even the scattering length drops out more or less, then you can describe all sorts of different systems, no matter what the energy scale is, the absolute energy scale is. Okay, so any questions at this point?
In the BEC limit, where can we see the gapless phonon modes, like from the Goli belt?
Yes. Okay. Yes. So that's the thing. Yes. So what? So what I've been. Okay. So what I've been discussing here, there were pair breaking excitations of zero momentum pairs. What? I guess where what you're describing here, what we'd need to do in order to see these phonon modes in the BEC limit is to actually now go back to this kind of parameter here, this fluctuation parameter, and consider now finite momentum fluctuations of this order parameter. So rather than just considering zero momentum like we considered here, I would need to actually go and start considering what happens when I have finite momentum of this paired these paired fermions, and that's what will give rise. Okay, I won't go into the details, but that's basically what will allow you to extract the dispersion of my phonon mode of my Bogoliubov kind of, or certainly in the BEC limit, then this naturally connects to the Bogoliubov modes that you're describing. Yeah. Does that make sense?
Maybe I missed it during this derivation, but it seems like we are still summing over Q when you follow through writing this interaction Hamiltonian.
Yes, but I think the key thing is what I did is I only took Q equals 0 here. Sorry, maybe let me make this clearer. So, well, okay, let me see. So what would be the best way to, let's see. So, sorry, I'm just thinking what's the best way. So yeah, so what you can do, so either, okay, so what would probably be this, what would be the easiest is if I'd say kept the Q dependence here. So rather than just only taking the zero momentum case here, I should have perhaps considered fluctuations of this field that involved finite Q. And that would, I think, allow me to actually look at finite momentum as well, and extract this kind of excitations at finite momentum.
Meera, similar question perhaps to that. So there are excitations that are not necessarily pair breaking. So for example, the Higgs mode, how can be seen there?
Yes, yeah. So basically, no, you're right. So exactly. So that's So that's exactly right. So you would need to actually consider, rather than just kind of like, okay. So basically you would need to not just, so this delta here, so I've taken it to be real, but in principle, I can consider both. If I considered it to be a complex kind of parameter, I could consider both fluctuations in its phase and fluctuations in its amplitude. Yeah.
Exactly. Yeah. But this, for example, I think in the Hamiltonian that you have, I mean, if you put the one on top here, you have delta. I mean, if you make it a complex quantity, it's still going to give you answers. I mean, the dynamics or some excitations, you can get it from there. I mean, not necessarily even going to finite momentum, but it's still there, giving you some excitations for, as you said, for a complex delta.
Well, you need complex and you need spatially dependent or finite Q delta.
Yes.
So what your Higgs mode is a fluctuations of the Cooper pairs of the bosons. And so you need, in addition to the fermionic excitations, you need just collective excitations of delta itself, not just the constant mean field delta.
Yes, but
then you would have an XY Hamiltonian for delta operator. If you wish delta, there's a delta fluctuation, meaning there are fluctuations of delta at non-zero Q, and those are operators. And those would be bosonic Hubbard model Hamiltonian of a type. And that would give you all the bosonic physics sector.
Yes, but Leo, I'm thinking for example, if I write this Hamiltonian in terms of Anderson spins, I have something that this Hamiltonian on top that I have there, the delta is plus capital. I mean, I have a creation. I can get this Higgs mode from that Hamiltonian, not? So if I have the interaction term, I write in terms of Higgs of Anderson pseudo spins, and I try to solve it for still only all to all exactly this Hamiltonian. I will get the dynamics of the Higgs excitations, yes?
You need the finite Q, I believe.
Really? No.
Otherwise, what you have is the total. It's sort of like having a single boson, single Higgs mode, like in a cavity, only one mode. But really, you have many Q modes that are excited. Very much like if you have a bunch of elementary bosons, Higgs mode is the fluctuation of those bosons.
Okay, so maybe the point that I make, if for example, with Victor, when he solves this equation of motions for the time-dependent superfluids, he gets oscillations of the Higgs mode starting with that Hamiltonian without other Qs. So he writes the H interaction, he look at the dynamics of this Hamiltonian, and he can
at zero Q. But
at
they're
zero
at zero
Q.
Q.
Yeah,
Yeah,
at zero Q.
I think when you change G values, you will get like a Higgs mode, right? Is that?
Oh, like a quench kind of.
Yeah.
Yes, if you change your G or your exactly. So you can get some that's what I mean, because that's the type of excitation that we get in the cavity when we simulate this Hamiltonian. There we can get this dynamical even with this Hamiltonian, yes? Or is that not correct?
I think you're. Oh, sorry, go on. Yeah, but I think maybe you're right that I suppose what you're saying is you're essentially exploring this kind of.
Exactly.
Yeah. So exactly.
What I would say is, it's a little bit of semantic question. You could call it a Higgs mode, but if you're going to include fluctuations of delta, okay, then you might as well, or you should, for consistency, include fluctuations of delta not just at Q equals 0, but at all Qs.
But these are not higher energy?
Well, there's a continuum of Qs, right?
Mm-hmm.
Qs, there's a dispersion for bosons with a mass 2m. So there's going to be a dispersion of those Qs, and they go all the way down to 0. So what you're doing by just considering Q equals 0, you kind of saying, I have a single boson describing my whole condensate, and that single boson can fluctuate.
Yeah.
Like the total thing can fluctuate. That's true. That's like saying I have n bosons in my condensate, with n being capital N, and then there's a conjugate phase phi. So then that's just like a single site problem, like a zero-dimensional problem.
Yes.
But if the full problem, like if you want to say like what the Higgs mode is in field theory, that's a particle that's dispersing. It has a mass of 4m in this context by Galilean invariance. And so then that includes its full kinetic energy, Q squared over, 4m dispersion.
So
and
in
that would be,
So in the experiment, when they said that they are seeing the Higgs mode and they were solving the Hamiltonian at 0Q, so in the palm probe experiments, when they said, we have evidence of the oscillation of the Higgs mode, when they solve the Anderson equations at 0 momentum.
Yeah, so they're seeing the 0 momentum limit of that mode. That's right.
Okay.
Yeah.
Yeah, and I think obviously, I think it also depends on where you are in the crossover, how accurate that it is to just only consider zero momentum pairing, fluctuations of zero momentum pairing, or whether you need to actually worry about these kind of fluctuations. Yeah, so BCS side, I think it's reasonable, but as you go towards unitarity in the BC side, then you need to worry about finite momentum pairing or fluctuation. Okay. Yeah, is my impression. Yeah. So maybe, sorry, coming back to this Boglebuff question. Yeah, so probably maybe perhaps the more precise answer is when I said I should keep finite Q, I should not drop the higher order terms at this point. I think is what I was saying, if I want to include kind of fluctuations due to this. Yeah, I need to include extra terms to describe the sound modes. Yeah.
Exactly.
Yeah. Okay. Cool. Any other questions at this point, or shall I? Let's see, where am I? Here. Yes. Yeah, it's kind of a very rich problem. Even though it's the basics are sort of simple to write down, but there's a lot of rich physics at the mean field level even. So I haven't even got to spin imbalance. Yeah, I think what I would, okay, since I'm getting short of time, the only thing I wanted to add really, so we've discussed a lot about, the ground state and for the unpolarized case. The only final thing, maybe I'll just pose a question here, is, so question is how, thinking about how comparing, condensation be destroyed. And well, okay, and I guess really there are two ways one can well, okay, I can put down two ways that one can do it, and well, the first one is finite temperature, and the second one, even if you're at zero temperature, would be spin imbalance, at least in the case where you have weak pairing. So I guess, yeah, I mean, I think I'm probably not going to go into many details of that, given that I'm running short of time. But let me say in general, I mean, it sort of comes back to what we were discussing over here about, this, how you can think about the free energy as a function of delta and so forth, and what's the structure of the thermodynamic potential of the free energy in general. So it turns out let me just write down, if I consider to begin with, say, finite temperature, what happens in that case? Oops. Okay, so finite temperature now, I start to get occupation of these more occupation of these pair breaking pair breaking excitations. So you can even go ahead and you can write down, so if I write down what this, let me call it this thermodynamic potential here, like write it like this, I can even go ahead and write down what that is, which is just, okay, so I use my usual kind of zero temperature, well, ground state term here. And then I have now a term that it essentially corresponds, at least at this mean field approximation, a non-interacting gas of these pair-breaking kind of quasi-particles, these gammas that we were talking about, with excitation energy EK. And so now what you find now is that in this case, you don't always have, so remember in the zero energy case, zero temperature case, we were always having something that looks like this. Yeah, I kind of just even here. So remember, that's what we're discussing. So there's always have something where the minimum occurs at finite delta. So you always have you always have pairing, you always have some condensate of pairs or superfluid in this case. And so this is true certainly for T below critical temperature, but you can find that above a critical temperature, then you find that you have a zero, the delta goes to zero basically at this point. So now the minimum is at delta equals zero. So there's no pairing, you lose the paired superfluid. So the only thing, so basically what that means now, and let me just quickly draw this. If I have my T over, and this is the Fermi temperature here, I have something that looks, if I draw this, let's go out to the BCS side here. So this delta, so here, okay, so this has this delta equals zero line, and now if I keep continuing actually that up, you find, okay, this is basically telling you the temperature at which you break pairs. So on the BCS side, where pairing is weak, that indeed does determine when you actually destroy your superfluid, your condensate. But now you know that on the BC side, actually, this becomes on this side, there's now a particular temperature now that's set by the density, right? So that's, you work it out, that's about 2 minus TF on this side here, 0.22. So at some point, this idea of, at some point the critical temperature is no longer determined by pairing. Okay, so actually you have something that looks more or less like this here. We have a maximum in the middle, which actually, well, coincidentally or not, roughly corresponds to this crossover point where the chemical potential is 0 here. So so what you're seeing essentially is that now, and this is coming back to the discussion we had about Bogoliubov excitations, on this side now, the critical temperature is determined by finite momentum pair, fluctuations of finite momentum pairs, and you're no longer having a condensate at 0 momentum. Whereas on this side, it's determined by the breaking of pairs, where pairing is weak. Okay. Yeah, so I think I didn't quite manage to get to spin imbalance, but I figured this might be the case, but I'm happy to take any questions about any of this or anything about, happy to have it. Maybe I'll just see if people have any particular interest in this or spin imbalance. I'm happy to discuss anything. Yeah. Everyone's getting late.
Yeah, maybe people are tired.
Yeah, I can understand.
I do have a question about so you gave an estimate for a mean field theory estimate for this crossover where mu is 0.
Yes.
And you said that like if you do a more sophisticated calculation, you get something roughly the same. Is there any way to see this in experiment?
Yeah, that's a good question. Has that been looked at? Yeah, actually, I feel like this is something.
Martin Zwerlein looked at it very carefully.
But I don't know if you looked at the crossover point, like this.
No.
No, I thought they studied all the thermodynamic quantities, chemical potential,
but not at 0
polarization.
temperature. Not at 0 temperature, no?
Yeah, and I thought it was speaking about unitarity, right?
Well, this is all 0 temperature.
Exactly, but I don't think Martin is so cold that he could use. I don't know, but I think he uses a lot of things at unitarity, but not the.
Okay, it's worth if you wanna. The best reference I know is Martin Zwerlein's sort of, he calls it precision, measurement of equation of state and things like this. And so I think experimentally that was the best stab at trying to, really precisely measure these quantities.
Oops.
At unitarity, he did beautiful work, but at unitarity.
But I don't know what you mean at unitarity. I mean, this is at finite density.
I mean, unitarity means very close to the KF going to infinity. I mean, at the unitarity point. That's what I mean, unitarity.
Well, I mean, it's once you're at finite density, unitarity it's not really a special point. It's, it's once you're, in a gas at finite KF, it's a crossover. So, there's no special point.
Well, okay, this is as close as you can get.
Yeah.
But yes, but yeah, no, I think I could be wrong, but my impression is this could be explored a bit more experimentally, actually.
I agree. I agree.
Yeah. Because this, for instance, is also important, say, if you go to lower dimensions like 2D, where, then, okay, so people had roughly been thinking of the unitarity point, even like Leo says, it's not like necessarily a special point in the crossover apart from being universal. It's not a special point in the crossover because, even though it designates where a bound state appears, it's not, once you have a finite density, that's not where, that doesn't correspond to a bound state appearing anymore. But certainly in 2D, certainly it's been used as a rough guide of roughly where the crossover is, or roughly what defines BCS and BEC. 2D, that's a little bit more problematic. You don't have that. But there we've been arguing that this is actually quite a useful way to actually define where you are with respect to BCS and BEC side, where the chemical potential goes to zero, roughly, at least in theory and also in trying to analyze experiment. Yeah. All right, so any other questions? Although I'm conscious that this is a
Can I maybe just a curiosity question?
Sure. Yeah.
At this point, when the chemical potential goes to zero, does the dispersion relation becomes k to the 4, right? So that's kind of slightly different from what one is used to. Is there anything interesting that can emerge there?
Yeah, no, actually, that's a good question. I think, yeah, so something we looked at, now I'm just trying to remember, this was a while back. Yeah, because in principle now you have, I think you can argue there's like a density of states divergence. Yeah, it's possible it might show up in some kind of spectroscopic measurement. I'm just wondering, yeah, I'd have to go and look. I mean, I can send you a reference. I think there was something where we even were looking at this exact point. Because I think in principle, I think you can even argue actually, okay, so this is a crossover, but this point even corresponds to, I think you can argue it's even a very high order, I mean, not a second order transition, but a much higher order transition in your problem. But yeah, I can go and if people are interested, I can dig up, not just my references, dig up a whole lot of references that people might be interested in.
Yeah, that may be helpful, and maybe send them to Daphne, and then she can post them as a supplementary material.
Yeah.
Okay.
Yeah, we can put it on the website.
Okay. Sounds good. All right. Cool. So I think thanks.
Thank you.
Thanks everyone. Thanks.
Well, thank you, Meera.
Thank you, Meera. Thank you very much.
Yeah, no,
Yeah, these were very, very nice lectures.
Very useful. Yes, very nice.
All right. Thank you.
Hope all of you also have a great weekend. Unfortunately, it's not here in Boulder, but hope you can enjoy a nice break and get ready for an exciting next week of the summer school.
Yes. Recharge your brains.
Please get some rest.
Yes.
We're gonna work
Monday is going to be a heavy day. If you have seen the schedule, there is one extra lecture added. That is great, but
by popular demand, I should say.
Yes.
Okay, perfect.
Okay.
Great.
Okay, bye everybody.